Alright, so let's begin with our pre-calc. We're looking at the kind of the intro to pre-calculus after our review. And we are looking at just kind of basic functions of graphs and where they're increasing, decreasing, and piecewise. Alright, so let's begin. Okay, so let's start off with increasing. So a function is increasing whenever if the x values, as the x values increase, the y values also increase. So if the graph looks like it's going up, straight line, curves, anything like that, that means it's increasing. And so when we're talking about increasing, we're saying as the x increases, the y is also increasing. So if, as a goes to b, b is the larger one, then that means that for the f's also. So f of a and f of b, f of a is smaller than f of b. Decreasing is just the opposite. So as the x's increase, your y's are going to be decreasing, which would look, it dropping. Okay, so nothing too crazy, nothing too complicated, but all those would be examples of decreasing. So as the x increases, the y decreases. As the x increases, the y decreases, which the reverse is also true. So if the x is decreasing, then the y has to be increasing. So it's just the opposite of each other. Okay. All right, if it's constant, that means as the x increases, the y stays the same. Okay, so as the x increases, the y stays the same, which is just your horizontal line. That's all this is saying. Okay, so one thing you'll notice with pre-calculus, moving away from algebra 2, is that you get more, going to turn into more formal writing mathematics-wise, using f of a and f of x and different things like that. Okay, so if we look at this graph, we want to identify, okay, where is this function increasing? So from what point to what point is this function increasing? Okay, so take a second and identify where this graph is increasing or where the graph is going up. Okay, so this would be increasing where the graph is moving upward. So we would say that it's increasing from, looks like about negative 1, 2, 3, 4, 5, 6, 7, negative 7 to positive 1. No, we don't want to zoom to positive 1. So that would be where an increase would be. And it also is increasing down here. So at 1, 2, 3, 4, 5, 6, 7, 8 to 10. So from 8 to 10, it's also increasing. Okay. So that means it's decreasing. Okay, so let's use a different color. So it would be decreasing from negative 9 to negative 7. Right here, it's decreasing, and it's also decreasing right here and right there. So it's decreasing from 1 to 3, and then 6 to 8. So those are all your decreasings. And then last but not least, it is constant from 3 to 6 would be where it's constant. Okay, so just identify, looking at the graph, it's just where is it going up, where is it going down, and you just write your points from your domains from the x to the y. You don't really worry about the ranges so much when you're identifying increasing, decreasing. You're worried about the domains. Okay, relative max and relative mins. So relative maximums are anywhere within a given interval for a function. The relative maxima exists when the c is an element of I, so it's a part of the interval, and the x is all points in I, and c does not equal x. C of x is greater than, or f of c is greater than f of x, and then minimum is the other way. Basically what this is saying in math jargon is that if it's the highest point, so if within an interval, so if this is my interval right here, so from 1 to 3, okay, 1 to 3, that's what it looks like. If at 2, the f of 2 value is larger than any other number on either side of it, then that is a relative maximum. Okay, Relative minimum, same thing. It's just the reverse. You're going for, it's the lowest number. So if this is from 5 to 7 and 6 is the lowest point, that means 6 is the relative minimum. So you're looking for any types of peaks or valleys for your relative maxes and your relative mins. Okay. So looking at this, do we have any relative maximums or minimums? So with this, how many relative maximums do you think there are in this image? Relative maximums. Okay, with this, there's one relative max. And that relative max is located right there. It's the highest point out of every other point on either side of it. It is also what would be called the absolute maximum because it is the highest point of the entire graph. Nowhere else do we have this little bump, kind of a hill that's being formed. That would be the relative maximum. Okay. So now, how many relative minimums do we have? So how many relative minimums do we have? And the number of relative minimums we have is 2. So we have a relative minimum right here because it's the lowest point on either side. It drops, it hits a low point, then it goes back up, and then we also have one over on this side. So we end up having 2 relative minimums. Okay, lowest point on either side. This, the one that just has the box around it now, is the absolute minimum. It's the smallest number of the entire graph. Okay. Let's look at a problem. So problem number 1. So now we're going to be looking at some word problems, identifying, writing a function, and everything like that. So Alan and Trey went camping. They took 2 cars because Alan didn't want to listen to Nickelback on the ride up. After the trip, they decided to take different routes or routes. They leave the site at a 90-degree angle. So if here's the site, one's going this way, one's going that way, creating a nice 90 degrees. Alan leaves at 65, Trey leaves at 55. Write a function to find the distance between the 2 cars, and then what is the domain of the function. Okay. So take a second and try to figure out what the function would be for this. All right, so with this, if we want to find the distance, so if here's our campsite, Alan is leaving at 65, Trey is leaving at 55, okay, in that direction. We want to find the distance between them. That distance is going to be right there. Well, what's the shape that we've just made? We've just made a right triangle. How do you find the distance of the hypotenuse in a right triangle? A squared plus b squared equals c squared. So we're going to use that equation. We're going to use formulas that we already know to help us answer this. So 55 and 65 are our a and b. So we'd have 55 squared plus 65 squared is equal to c squared. And that can be our formula to find the distance after 1 hour. Now the problem is that we don't know how many hours. So what we would have to do is that we'd have to add a variable. I'm going to use x because x is my number of hours. And to find the distance they've traveled, you would take the number of hours they've driven times how fast they're going. Okay, so it'd be 55x squared plus 65x squared is equal to c squared, which ends up being their total distance. And that right there would end up being our function. You could solve for c, which would just put a square root over the 55 and 65 part, or you could keep it like this. Now the next part is asking about our domain. What's the domain of this? Well, what's the least amount of hours they could drive? So for our domain, so the least amount of hours they can drive was 0. Okay, they could drive no hours. What's the maximum? Do we have a limit on how far they could drive, how long they could drive? No, we're not told a limit of how long, so that means that we would say it's infinity. And so we'd include the 0, but we'd exclude the infinity. Okay. And so that would be our domain. We'd write that interval. Okay, let's move on to our second problem. So Kate just got a pet turtle. and she wants to fence. She wants to basically build a fence so that the turtle has some space to roam around. Um, Two of the walls of her fence are going to be part of the house itself. So she's building up against kind of a inverted corner in the house. She wants it to be a rectangle, and she only has 40 feet of fencing to use. So write a function to find the greatest area. What is the domain and range of the function, and what's the dimensions of it? So our goal is to find the largest dimensions for this. So again, how this is set up is that, let's say this is her house. Her house kind of looks like this, and she wants to build the fence right there. And so she's only going to use fencing for that orange part. The part along the house she doesn't need to worry about. Okay. So write a function to find the greatest area. Remember, to find area is length times width in a rectangle. Find the domain, the range, and then what is the dimensions of it. Okay. So take a second and see if you can find what the dimensions would be to find the greatest possible area. Okay, so using this, so again with our setup, here's their house, and then the orange is going to be the walls that we're going to use. Now, to find area, we need to use length and width. So to find the area, we use length times width. So area is equal to length times width. Now with this, we also need a second equation. That second equation is going to be length plus width. And what's the maximum length that that fencing can be? That fencing has a maximum length of 40. So length plus width has to equal 40. Can't be more than that. Now what I'm going to do is I'm going to solve for W. So I'm going to subtract L on both sides, getting me W is equal to 40 minus L. Now once I have that, I'm going to take this and plug it into the W in my area equation, because what I want is I want everything as one specific variable, which puts me at the area is equal to L times 40 minus L. And there's my formula to find my area, given only a certain length. I don't need to worry about what the width would be. Now you can multiply this through and you can use another one. Area is equal to 40L minus L squared. Okay, that would also work. Now if you know what that graph looks like, it is a parabola that's opening downward, which means we have a maximum that's occurring. And what we want to do is we want to find that maximum. So first, let's see if we can find our domain and range. So there's our formula. That's the first part that we were looking for. So now let's do our domain and range. So for our domain, so our x's, or our l's in this case. So for L, what is the minimum you could have for your length? So what's the smallest length you could have? Smallest length you could have would be 0, because you could have no length. Okay. What's the largest? So what's the longest you could have? The longest, you could use the entire fencing for it, which makes it 40. And so we would include both of those because we can actually get those numbers. We can have a length of 0, we can have a length of 40. Okay. So now let's do our range. So our range is going to be the areas. So what's the smallest area we can have? So if we have a length of 0, that means one side's 0, the other side's 40. 40 times 0 is 0. So that means we can have an area of 0. So the next question is, what's going to be the maximum area we can have? And that's where we would take this graph and we want to find where that peak is. Okay, we want to find where that top point is. That top point ends up being at about 400, or it is 400, it's not about, ends up being at 400. And so where does that occur? Again, solving it, finding it. You can graph this on your calculator, use the maximum minimum function on your calculator to find it. Going through solving it, you know that your dimensions end up having to be 20 by 20. Okay, so if the length is 20, the width also has to be 20. Okay, so now let's look at this. What kind of function is shown here? So we've got multiple different functions we can use, linear, so on and so forth. But this is a special type of function because it's not linear, it's not exponential, it's not a quadratic, it's kind of a mix of multiple things. Looks like there's kind of a sine curve, there's a line, and there's a parabola all snuck in all together. This type of function is called a piecewise function. And so a piecewise function is where you have multiple functions put together to create a single function. Okay, so it kind of changes as you move along your domain. So this example down here, this f of x, is an example of a piecewise function. So you see the first part right here, x minus 8, that is an actual function itself. Okay, that's the function, and then the second part tells you what the domain is that you're going to be using. So we're going to use x minus 8 from where x is less than 3. So all numbers less than 3, we're going to use this function. Okay. The next one we'd use from 3 to 5, and last one we'd use for greater than 5. One thing you want to watch out for is that if it has the equal to, okay, those are going to be filled in circles at those points. If it's not, then you're going to use open circles at those points. And that's mostly if you have what's called a discontinuous graph or a disconnected graph, that comes into play. Okay. And we'll look at that in a few slides. So let's look at this, and let's say we want to graph this. So what you want to do is you kind of want to find out where's the points that it's changing kind of to start. So starting with the first one, it starts to change at 3. So we're going to go to 3, and then we're going to plot our points. So if we plug a 3 into this first equation, we end up with a negative 5. 1, 2, 3, 4, 5. So we're going to be there. Okay. And now what's happening when it's less than that? It is a linear function. Not great, but close enough. So it's a linear function with a slope of 1. It actually should be a little bit flatter for that. Okay. Now, let's change colors and do the next one. So the next one, we go from 3 to 5. So if we plug in a 3, we see that we get the exact same point. So that means it's a good start for us. It's going to be connected. When we plug in a 5, we end up with a negative 1. So 5, negative 1. So right there. And then we just connect those. It's also a linear function, so we're just going to draw a straight line again. And then last but not least, we're going to use our last function. So plug in a 5 to see what we get. When we plug in a 5, we get negative 1 again. So that means we're starting here. And then it's a parabola opening upwards, so I'm going to kind of curve it and have it going up like that. So how this looks like is that we have a flat, we have a linear function, another linear function, and then we have a curve going the rest of the way upward. And you can graph more points in between to help you. Mine was just kind of a rough sketch for that. But a piecewise function is multiple functions that are being pieced together. Okay. All right, so continuous and discontinuous. So with these piecewise, we have to look out for what are called continuous and discontinuous graphs. A continuous function or a continuous graph is a graph that has no holes or asymptotes. So if it's a nice, smooth transition, So if it's a nice, smooth transition from the previous one to another. So that would be a continuous graph. Yes, it does change, but it's still continuous. Okay, so there's no jumps in it. Okay, a discontinuous line or function is where you have asymptotes or holes, you have breaks somewhere. So so if you have something that looks like this, that would end up being discontinuous because it's not connected. If you start up here and then it jumps down here, that's also discontinuous. It's broken. Okay, and this is real important when you start doing calculus because you need functions to be continuous and differentiable. So continuous just means that it is connected all the way. There is no holes in it anywhere. Okay, so that's continuous and discontinuous. Next up, we have our greatest integer function. So our greatest integer function is just a function that you probably haven't seen very much of, if ever. And so there's floor and ceilings. This is a floor function because it's the greatest integer. So what ends up happening is um, whenever you have a number that has some sort of decimal, 1.4, 1.9, 3.6, anything like that, what you do is you always round it to the greatest integer that it has. Now, what that means doesn't mean you round up, it means you round down because the greatest integer that that number falls into. So like 3.6 covers all the way up to 3, but it doesn't hit 4. So the greatest integer you have is 3. So this is why it's called a floor function, because you take all the numbers and you drop them. Right here are 3 different ways of writing it. Okay, you'll see it written 3 different ways. As you see with this one, it's a floor function. It's got it underneath. But what ends up happening is that every point that falls between, let's say 0 and 1, just gets rounded down to 0. Every point from 1 to 2 gets rounded down to 1. Okay, and so on and so forth. They just all fall to the lowest one, and you end up with this little step. These are also called step functions that we have. So this is for the greatest integer. So you'll see it's got kind of this double bracket, INTX, or that bracket with just the floor on it, the bottom one. So this is again rounding down for it. Now you also have our we also have a ceiling function. But first let's talk about what our domain and range is for this. So if we're looking at this and we're asking what's the domain, okay, so the x values, are every x value talked about in this? And the answer is yes, every x value. So for your domain, you could say that it's x is all real numbers. Okay. So x is all real numbers. X is the set of reals. There's different ways of saying it. But since every x value can be counted, we end up having every x value, all real numbers, are part of the domain. The range, on the other hand, if we're talking about the range, okay, the range, if you see here, we have 1, and then we have 2, and then we have 3, and then we have 4, and we have 5, and then we have it also in the negatives. So with this range, you would have to say all integers. Okay, you have to be specific. Okay, so it's only integers in the range, not all numbers, because 0.5, 1.6 are not a part of it. So if it's only integers, you have to specify that it's only integers in this one. Okay, so ceiling and floor functions. So again, these are step functions that are just different. So you see the functions are slightly different. So if you notice, the ceiling just has the brace on top, while the floor has just a brace on bottom. And so that tells us if it's a floor or ceiling function. Now, when you graph them, okay, you'll notice there's a few differences. One, at 0, so from 0 to 1, it is at 1 for your ceiling function, because everything's being rounded up. Okay, so everything's being rounded up. And your floor function, everything is rounded down. Okay, so that's why we say ceiling and floor. Ceiling, you go up. So if you have a decimal 0.4 and a ceiling function, you would go up to 1. And a floor function, you'd go down to 0. Also, you notice with the dots, so the open and closed circles. The open circle means that you don't include that one. You basically approach it, but you never touch it. The closed means that you include it to that one. So if you see these, for their ceiling function, the left-hand one is always open, while the right is always closed. And for a floor function, the left is always open, while the right is always closed. Okay, for your ceiling function. All right. Okay, that's the end of this first section, which is a very long section, I know, in this chapter 2-ish. Kind of your intro to all these basic functions for graphs.